Hi everyone, my name is Yichen and I'm a solutions architect here at AWS. Thanks for joining me today for today's session on event-driven processing for data analytics. In today's session, I'll first go through the differences between batch and event-driven processing, followed by the main two components of an event-driven architecture, which are event routers and event stores. Then I'll cover event processing, and last but not least, we'll have Nikhil from Autodesk, who will share Autodesk's story on migrating its data pipelines to an event-based architecture. If you look at the lifecycle of a typical data pipeline, there are mainly 5 stages. It starts with ingestion of data in stage 1. It can be the uploading of files or stream of data which is based on events, such as user clicks on a website, telemetry data from machines, or even transactions from a payment system. The second stage involves cleaning, preparing, and cataloging the data. So steps like removing duplicates, adding additional fields comes under stage 2. In stage 3, the data is then loaded into different data stores and security policies are enforced. The data is then made available for analytics in the 4th stage, and finally archived after it has gone old in the 5th and final stage. We'll be focusing on the first 2 stages in today's session. The processing stage is traditionally done on a batch basis and for very good reasons as well. Let's first take a look at the characteristics of batch processing. The data is first ingested in events, hence you will have tons and tons of small files or messages. It is then accumulated till it reaches a significant amount before it is sent for processing. The processing is run on a schedule, for example, once a day or once every hour. By accumulating large volumes of data before processing, batch can actually leverage on economics of scale, hence increasing efficiency and better utilization of compute resources. When the batch job is done, the infrastructure can be utilized by other jobs, or it can be brought down if it's hosted in the cloud. This will lead to further efficient use of compute resources. However, batch processing does have its own set of challenges. First, because you have to accumulate enough data, there is a time delay between data collection and data processing. It can range from an hour to even days depending on your batch schedule. This delay will then trickle down to the later stages, including analytics, which might result in dashboards that are lagging behind the data in real time. Also, the amount of data influx can differ greatly from peak hours or from weekdays to weekends. Provisioning just enough resources to process the data for each time window is challenging, and companies often find themselves provisioning for peak. Sometimes it just takes one event out of a million that can result in an error and cause the whole batch job to fail. This is typically known as a poison event. Reruns can be expensive, and mechanisms to resume jobs from where it left off can be hard to implement. Hence, there has been a large movement towards event-driven processing as it addresses these challenges. Unlike batch, events are processed as soon as they arrive, either individually or in very small batches, such as a minute time window or a batch of 100 events. This would then enable real-time analytics or dashboards. The second characteristic is that events can be processed in parallel or asynchronously. Hence, the compute that processes events can scale horizontally instead of provisioning just a bigger machine. In order to do that, computations have to be independent of each other. And because they are independent of each other, errors can be self-contained within each computation. Hence, you no longer have the problem of a poison event. Not to say event-driven architectures doesn't have its own set of challenges, but AWS services do make it easier for you to implement them. First, event-driven architectures often consist of distributed components, and orchestration of these components can be hard. AWS makes it easier by having tight integrations between AWS services. Also, Scaling and ensuring reliability of each component can be a chore. So do leverage serverless services, which reliability is already built in, and the heavy lifting of scaling is taken care of. Now, let's take a look at the different components of an event-driven architecture. First, there are event routers which abstract producers and consumers from each other. And then there's event stores, which buffer messages until the processing services are ready and available to process the events. Let's take a look at an example. When a client makes a request to a web service, let's say to make an order of an item, the web service will then acknowledge the request and sends an event downstream to an event router. It can then route the message based on rules to an event store, which the appropriate service will then pick it up. Since it is an order to be fulfilled, the rule engine will route to the fulfillment service. If it's a user action such as clicks and views to be analyzed, the rule engine can route the events to the analytical service. So why do we need an event router? Can't you just post the event to the consumer directly? In a single producer and consumer situation, yes, you can do that. However, things get complicated when you have multiple producers and consumers. It becomes very cumbersome to manage these many-to-many relationships. Hence, an event router is actually a much more scalable way of managing events. It acts as a central hub for producers to send messages to and uses a rule engine to route events to consumers. In AWS, there are three main event routers. The AWS native ones, and also serverless in nature, are Simple Notification Service, SNS, and Amazon EventBridge. SNS utilizes topics and filters, whereas EventBridge is an event bus with a rule engine. Also, Amazon MQ is a managed open source offering of Apache ActiveMQ. So, how do you choose between EventBridge and SNS? A general rule of thumb is that if you have less than 5 targets, EventBridge will be the choice, and it has a more robust rule engine of up to 2,000 rules per bus. Also, EventBridge has a much lower latency in seconds compared to SNS, which has up to 50 minutes of latency. EventBridge also supports a larger range of targets natively and supports third-party sources like Zendesk, Datadog, and PagerDuty. On the other hand, if you need to send events to more than 5 targets, maybe to hundreds or even thousands, or have SMS as one of your targets, SNS will be the event router of choice. Now, let's take a look at event stores. Event stores buffer messages until the processing service is available and ready to process them. This ensures that the processing service is not overloaded, especially when there is a sudden spike in events. It also gives the processing service time to scale up and down, depending on the number of messages in the event store. There are mainly two types of event store. The first being message processing, which Amazon SQS and Amazon MQ falls under. In message processing, messages are processed individually and are deleted after successful consumption. Because of that, there's no need to track the position, as there will only be unprocessed messages in the queue. After a certain number of retries, failed messages go into a dead letter queue. The second type is stream processing, which Amazon Kinesis and Amazon MSK, which stands for Managed Streaming for Kafka, falls under. In stream processing, messages are processed in micro batches and are available after consumption till the messages expire. Hence, the consumer will need to track the current position in the stream to avoid processing the same message twice. Alternatively, you can have two different sets of consumers processing the same stream of messages, as messages are not deleted after consumption. For processing events, there are two main ways in which services can consume events. Services can be run on any AWS compute, which includes virtual machines on EC2s, on containers using ECS or EKS, or on Lambda. One way is through asynchronous request, which is essentially a push. The push can be triggered via SNS or event bridge. S3 can also push an event whenever an object lands into a bucket. One downside of pushing is that the downstream service is making a commitment that it has the capacity and will be able to handle the oncoming requests. Hence, modern architectures actually prefer processing services to pull events instead. Having a buffer like an event store will allow the downstream service to pull messages whenever the service is ready. If you are already using DynamoDB, DynamoDB Streams is a good option as it will contain all the change events that happen on DynamoDB tables. You can then have Lambda or any compute to pull events from DynamoDB Streams. If you are using Kinesis Streams, Kinesis Data Analytics, which runs on Apache Flink, is a good option, especially if you need stateful processing capabilities. So you can compute things like total counts, what is the maximum or minimum over the stream. Now, I'll pass my time on to Nikhil, who will present on the Autodesk story.
Hi, my name is Nikhil Ashok Sharma. I'm a senior data engineer with Autodesk, and I'm happy to have you all joining us today for this session. In this presentation, I'll be sharing a story of how we migrated a batch EC2-based ETL pipeline to an event-driven serverless near real-time pipeline. Before we move on, a bit about Autodesk. Autodesk makes software for people who make things. If you've ever driven a high-performance car, admired a towering skyscraper, used a smartphone, or watched a great film, chances are you have experienced what millions of Autodesk customers are doing with our software. We have products for architecture, engineering and construction, product design and manufacturing, media and entertainment. Some of the top products are AutoCAD, Revit, Inventor, Maya, 3ds Max. A bit about my team. I'm part of Autodesk Data Platform's product analytics team. We collect, clean, enrich, analyze, aggregate, and present product usage data for all 75 plus Autodesk products. Talking about data volume, we handle around 10 billion events on daily basis, which is around 10 TB JSON data. We have built a data lake entirely on AWS and have integrated data from 10 plus sources. Talking about the big picture, at a very high level, our overall platform architecture looks like this. We have data being ingested from all Autodesk products running on desktop, servers, mobile, and web. We have SDKs sitting with our products, collecting data, and sending to a microservice. This microservice is front-ended by AWS Load Balancer running on ECS and is backed by Kinesis Firehose. This microservice sends the data to Kinesis Firehose delivery stream, which delivers the data to S3. Then we have an ETL hourly batch pipeline running as a Spark application on EC2s, which clean, enrich, and makes the data available in Parquet format for downstream aggregations. We are using Presto as our query engine and Looker as a BI tool. The ETL hourly batch pipeline that we talked about in the previous slide is the process that we migrated to near real time. Before we move into nitty-gritty details of the migration, I would like to give some context about the process. The ETL hourly batch pipeline, also known as the enrich-raw process, does following. It reads data from S3 in JSON-GZIP format, cleans the data in which it validates the schema, does data cohesion, and separates out garbage data. Enriches the data with geo information and customer information. Repartitions the data based upon when the event occurred on the client machine, and the final step is to write back optimized Parquet files to S3. Why Parquet? Because Parquet is a columnar storage, which means it stores data in form of columns instead of rows. which is done by JSON, CSV, etc. Hence, Parquet is very efficient in reading and performing aggregations on data. Also, Parquet supports compressions like Snappy, which has very fast compression technique, which makes it best in performance and lowest in storage. The obvious question would be why we would change something which was working for us. I would now like to list the reason why we needed to rethink about this process. With new data ingestions and improved adoption of our framework, we started seeing data surges. And when data surged, we started encountering problems with this process. Very first instance was when data surged by 3x. This is when this process started failing, and we had to spend 2 to 3 days to find optimal configurations for this process to be able to run for this data volume. Even with optimized configurations, the process could handle a max of 150 GB data per hour, and we were already at 130 GB per hour. And we were expecting more data to come in near future. This issue was a showstopper. The second point was the process was triggered to run for -1 hour and at 40th minute of the hour. And for average load, the process was taking around 2 to 2.5 hours to complete, which introduced a 4+ hours of delay in the data. Third point was the process was unable to handle data spikes and would fail in such instances. If the process fails, the data was missing for an entire hour and all downstream aggregation had to wait. Now, let's look at the most interesting and challenging part of our story, the actual migration. So we decided to redesign this process by putting on an entirely different lens of event-driven architecture. We started by decomposing the problem into smaller problems so that we can take an incremental approach. The entire problem was split into 3 subproblems: cleaning the data and identifying invalid, corrupted data, enrich clean data with geo and customer identification information, partition the data based upon occur time, and produce Parquet output in hourly tables. We replaced each problem statement with an AWS component that fits the best. So we implemented cleansing as a lambda, enrichment as another lambda, repartitioning as another lambda, and for the batch hourly support, we implemented a microservice with lambda as the callee. Let's look at our new architecture. In a typical event-driven architecture, we would have a data stream and a data stream processing tool to process events as they come. So typically, our lambdas would be listening to an event store like SQS or Kinesis data stream, as what Yichuan described earlier. Kinesis Firehose delivery streams were already deployed with microservice, and we didn't want to change our overall platform architecture. So, for our migration, we considered S3 object creation as an event, and all the processing starts when S3 object is created by Firehose. Our input data are the file written by Firehose in S3. These files are of fixed sizes, which is 128 MB, because we have configured Firehose buffer to be 128 MB or 15 minutes. So we were sure that the lambda will be able to process these files. We created a SNS topic and subscribed to S3 location for any S3 object creation events. And then we had a series of lambda to do the core processing per S3 file. For any failure, we had a dead letter queue configured and a lambda that copied the file to failed location. And finally, the batch support was provided by writing S3 file metadata to DynamoDB and having a lambda reading this metadata on hourly basis and sending request with input and output S3 file metadata to SQS. A microservice is listening to this SQS. This service reads SQS messages, downloads the S3 file based upon input S3 files metadata, converts JSON data to Parquet, and writes to S3 based on output S3 file metadata. The Hive tables are pointing to output S3 location, and partitions are managed by another microservice. With this architecture, the results that we achieved are marvelous. We tested the data with 1x data volume, that is 150 GB per hour, with 2x data volume, 300 GB per hour, with 5x, 750 GB, and with 10x data, that is 1.5 TB data per hour, and the new pipeline can process that data within 10 minutes. We reduce the latency of the data being available for consumption in S3 location from 4+ hours with the old process to under 2 minutes with the new process. Because we had modules for each subproblem, each module had internal retries and recovery processes. This made the recovery fast and automated. And finally, the selling point of our story was the cost reduction. We are now operating at a cost which is a 90% cost reduction over the previous process. Now let's look at a comparison of before and after. Before, scaling was manual and vertical. Data peaks needed manual interventions. Now, everything is serverless and scales with demand. Before, data delay was 4+ hours. Now, it was reduced to less than 2 minutes. Before, failure recovery was manual. Now, every module have automated recovery and retries. There were a lot of learnings and challenges in this migration, but I would like to share two of the most important learnings. First, lambdas are cheap in cost, but if we want to reduce the cost even further, we have to focus on reducing memory footprint and processing time of lambda. Because lambda cost is equal to processing time into memory. And these approaches can reduce the cost significantly. First is to reduce memory footprint while processing big data, we can use ephemeral disk as a temporary storage instead of holding everything in memory. There is one caution. The ephemeral disk is limited to max 512 MB. For small data, we can store the data in memory and stream in and out from S3. For reducing processing time, we can implement multi-threaded code. From our experience, Lambda machines are powerful and it can run multi-threaded code very efficiently. Caution: the code should be thread safe because Lambda instances are shared between different Lambda executions. Second one, which is extremely useful. While building asynchronous microservice systems, using SQS as a buffer for the service has many advantages. Like, retries can be easily managed with SQS visibility timeout feature. Failure recovery is easy as messages can live in SQS for up to 14 days. SQS queues can be monitored easily. Autoscaling of services can be achieved by using SQS queue depth. Also, SQS guarantees at least once delivery of the message, so no message is lost. With that, I would like to end my presentation. Thank you all for participation. Go Autodesk, go Eventdriven, go serverless, and go AWS.
Thanks, Nikhil, for sharing Autodesk's story. It is always great to know how AWS customers are benefiting from modern architectures. To gain more confidence and hands-on experience with AWS, access the digital training built by AWS experts. Attend our instructor-led classes by qualified instructors and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. Validate your technical expertise with AWS and use practice exams to help you prepare for AWS certifications. Thank you again for attending this session. We really appreciate your feedback. so that we can better understand the topics and services you would like to know more about. So please do take the time to fill out our survey and let us know what you think.